Okay. Now, we're still working on the homework, but the grades are posted for exam 2. You should have the grade report. You should see the grades on Blackboard. And all of the outstanding homework solutions are posted, except for homework 6.2. I haven't posted that one yet. I need to do that sometime today. But I want to talk a little bit about what is coming, not just between now and Thanksgiving, but between now and the end, to make sure that everybody's crystal clear on this. So today is our second and final lecture on shear and moment diagrams. And to also be crystal clear, today is the last topic coverage of exam 3. Exam 3 is going to cover centroids, trusses, and shear and moment diagrams. And that's what's going to be on exam 3. The final is going to be comprehensive with the addition of friction. So friction is not going to be on the next exam, okay? What we're going to do today is we're going to finish shear and moment diagrams. On Friday, I'm going to introduce friction at a probably very high level. What we'll do, and you'll find friction's really basic, really straightforward. There's probably not a lot that I'm adding to this that you didn't get in Physics 211, but I just want to make sure that you all have a good coverage of it. Sorry. What we're going to do next week, Monday, we're going to have our exam review, same as we had before. I'm going to post a thread on Teams for you all to be able to collate questions. We'll come in. If you have questions, please ask them. On Wednesday, we're going to celebrate. We're going to have our third exam. And Friday, class is canceled. Okay? Everybody okay with that? Now, what's going to happen when we come back for dead week? Monday on dead week, what we're going to do is we're going to sort of formally finish friction. What I'm going to do on Friday is I'm going to assign homework 7. Homework 7 is it. It is the last homework in the semester. Okay? Homework 7 is not going to be due until the Wednesday of dead week, so you got plenty of time to do it, okay? And it's not going to be any longer than any of the other assignments. It's going to be pretty much the same as assignments as before. And so homework 7 is going to be the last homework assignment of the semester. With one exception, I do have an opportunity for some bonus points on the homework average regarding a survey I want you all to do. Monday, we'll finish friction. Wednesday, we're going to have a comprehensive course review so that you all have an understanding of what's going to be on the final. Friday of dead week, we're going to have our Q&A session, our exam review. We come back next Friday, take the exam, and we're done. What do you think? You don't have to be that happy about being done with my class. So next semester is just going to be torture, right?
Well, I got you next semester. So
that's what I'm saying. It's going to be torture, you know? It's like you're so happy to be done with me just to have me again, right?
At 8 a.m.
At 8 a.m., yeah. Okay. Back to shear and moment diagrams. Okay, so last time, and hopefully the homework assignment was fairly straightforward in terms of the construction of shear and moment diagrams. Hopefully you kind of have an appreciation for the relationship that we use to develop our graphical approach. The idea that we are essentially integrating the load diagram or the free body diagram in order to construct the shear diagram, and then we're integrating the shear diagram to construct the moment diagram. And regardless of how complex I could, how funky I could make the loads, that is generally the process. That doesn't change at all. Okay. Now, these conclusions, the idea that at any given point the slope of the shear diagram is equal to the load and the slope of the moment diagram is equal to the shear, and how we develop values on the shear diagram, none of this is going to change. What we need to do is talk about distributed loads. Okay, distributed loads sort of ratchet it up a little bit in terms of difficulty, but it also ratchets it up a little bit more in terms of reality. So I think we need to handle this. Past this, I think if you can handle concentrated loads and distributed loads, you will be able to handle the vast majority of real-world problems that engineers face. So if you can handle these two, you're good in my book. Now, whenever we computed reactions, okay, if you remember, we would take a distributed load that looks something like this, and we would collapse that into a single concentrated load that was located at the centroid. So if I have, let's say 5 kips per foot over a distance of 20 feet, I would turn that into just 100 kips, right smack dab in the middle, right? We can do the same thing when we're trying to compute support reactions. But this is probably the most important point of today's lecture from a concept standpoint, and that is that when we do this, what we're doing is we're collapsing this into a point load to make the math easier when we compute support reactions. But then when we draw the resulting shear and moment diagrams, we have to recognize that this is the problem we were given at the beginning, not this. Okay, so we have to revert back to the original loading, okay, because that's what's going on the structure. The best way I can describe it so that you have sort of a physical understanding of what I'm talking about is if I had 1,000 pounds right here, what would be the worst case scenario for this table? To spread it out evenly across the length of the table or put 1,000 pounds right smack dab in the middle? Put it right in the middle. Now, from a statics perspective, it can be idealized as 1,000 pounds in the middle or spread out because both scenarios will tell you that each leg's got to hold up 500. But in terms of the distribution of load along the flexural component of the table, we need to go back to the way it originally was. Now, for the mathy folks in the room, if we have a uniformly distributed load, then we have a load that can be represented by a constant function. To construct the shear diagram, we must integrate that load. So if we integrate a constant, what is the integral of 6? It's 6x, right? Plus c, right? So whenever I integrate a constant, I get a linear function. And whenever I integrate that again, I get a quadratic function. So our moment diagram, so our shear diagram is not going to be stair-stepped under distributed loads. It's going to have an incline to it, okay? And our resulting moment diagram is going to be parabolic. It's going to have some curve to it. So we got to make sure we account for those regions when we construct our moment diagrams as well. Now, before we get into the problem, we're going to have to deal with this. And the last thing that I want is for some simple geometry to get in the way of what we're actually trying to do. So I got a little bit of a basic geometry problem here. I have a horizontal line, and I have this diagonal line. And the diagonal line goes from positive 25 to negative 75 over a distance of 25 feet. And what I want to know is what are the area of these two triangles. We're going to keep it simple, but I want to show you a couple ways of doing this, okay? And then we'll get into our real problem. So, let me ask you a question. If I were trying to determine the slope of this line, the slope of this line could be represented by the change in y over the change in x, okay? What is the change in x across that diagonal line? 25. What's the change in y? 100. Or, I mean, negative 100, but I'm not really worried about signs at this point. I'm just worried about magnitudes. So I propose that the slope of that line, 25, is 4 kips per foot. And notice if you actually follow the units, you get kips per foot, which it's kind of weird. Kips per foot, or it's kind of peculiar that kips per foot is the same units that you would utilize for a distributed load. The slope of the shear diagram is equal to the load. So normally on shear diagrams, we don't even need to worry about this because we know what the slope is from the loads, okay? But if we want to determine the area of these triangles, which that's a reasonable question given the fact that to construct the moment diagram, we must integrate the shear diagram. We need to determine these areas. What that means is we need this distance. Now, can anybody tell me a super simple way of computing that distance? Super easy. 25 over 4. Now, how are we doing that? Well, if slope is change in y over change in x, and I want the change in x, I want that horizontal distance, Just do change in y over slope. So 25 over 4. What is 25 over 4? 6.25. So what's this one if we were to use the same philosophy? Maybe 75 over 4? What is 75 over 4? 18.75. What is 6.25 plus 18.75? It's that. So how do we determine the area of a triangle? 1/2 of base times height. So what is the area of this first triangle? I just want to make sure we're comfortable with this. I don't want this to be a problem in our problem we're going to do here in a second. Say it again. Say it again. Do I have a second on that? All right, and this one. Do I have a second on that? Okay, good. Is everybody comfortable with that, like, geometrical riddle? Because that's going to come up, okay? Everybody good? Okay. If you're good with that, then let's actually do a real problem. So here's the problem that we're going to do. So I didn't want a problem that just had distributed loads. I wanted distributed loads and point loads, because here's the thing. Even a structure with just distributed loads is going to have point loads on it too, more often than not, because of the reactions. Okay. Now, speaking of the reactions, let's go ahead and idealize those. We have a vertical reaction right here, which we'll call AY, and a vertical reaction right here we'll call CY. Now, we got a reaction here that's AX, but what is AX? What's that? That is right. Now, let's talk about this distributed load. I have 3 kips per foot applied over how far? 60. So if I wanted to collapse that into a single point load, how much would it be? 180. And how far away from point A? 30. So this right here would be an idealization of that point load. Now again, and I really want to hammer this in, that 180 kips is a mathematical tool that I am using to make computation of support reactions easier. But that's what's not on the beam. I do not have 180 kips right smack dab in the middle of the beam. I have it spread out, which is what I'm interested in when I'm determining internal response. Just keep that in mind. Okay, now, hold on, let me move that over a little bit. So I'm going to sum moments at A, and this should be pretty rote at this point in order to determine support reactions. So I'm going to sort of do this one a little bit myself. So I have 3 loads applied on the top of the beam, 180, 30, and 60. And they are all generating clockwise moments, which is negative according to the sign convention that I've indicated here. So I'm going to have negative 180 kips times 30 feet minus 30 kips times 40 feet minus 60 kips times 80 feet. And notice, all these distances, the 30, the 40, and the 80, are how far we are from A, because this is where we're summing moments. And this is counteracted by the reaction at CY that is 60 feet away. And the sum of those moments must equal 0. Is that okay? Did I do that too fast, or are we good there? Okay. So 180 times 30, didn't mean for that to happen. Negative 5,400 foot kips. That's my little shorthand for foot kips. So if you're wondering what that is. Minus 30 times 40, that's minus 1,200. Minus 60 times 80, that's 4,800. Equals negative CY times 60. That's just moving that over on the other end. And so that gives me negative 11,400 foot kips equals negative CY times 60. So if I divide, I'm going to get a positive answer. I'm going to get CY is positive 190, or 190 kips going up. Like, is that okay? Did I do that too fast, or are we comfortable with that? If I need to stop and go through it, I am more than happy to, because we got plenty of time. My man in the back's worried about a different kind of reaction. Was that acid-base reaction? The technical term for that is busted. All right. Now, how do we determine the the remaining support reaction? With some forces in the y direction. So, with some forces in the y direction, we got AY and CY going up. Minus 180, 30, 60 is 0. Oh, sorry about that. So CY is 190. Oh, goodness, I'm bringing all sorts of windows up. Minus 180, minus 30, minus 60. And then chug that out, and we're going to get AY is plus 80. Let me circle these so that in the C of all this, math, we can see what we're talking about. All right. If I did that too fast, please do not hesitate to ask me where a value came from, where a distance came from. I'm just was thinking that at this point, the reactions we should be pretty comfortable with. But if there's anything I need to stop, don't hesitate. Everybody good? Okay, now here's the thing. Okay, I cheated a little bit, and I've got the image of the beam reproduced down here. So here's the beam, and I'm going to go ahead and reproduce my reaction. So this one is 80, and this one is 190. Notice how what I don't have on this image is the 180 kip idealization I just put down. Because again, that was a construct that I created to make the math a little bit more easier for me. But that is not in existence on the beam. What's really on the beam is a distributed load. So we're reverting back to the original loading. So let's go back to the construction of some shear diagrams. So remember how we did that before? All right. All right. Whenever we construct a shear diagram, as I said before, we start at 0, end at 0. That does not change because of this newfangled distributed load. It's the same story as before, okay? So, if I start at 0, what is the first thing I need to do? What?
80 minus 3 is 77.
Oh, I see what you're saying. Okay, all right. That's a very interesting point, and
Or
you're
80 and then continue at a slope of negative.
there you go. That's what that yeah. Let's explore that a little bit. So here's the thing, okay? This is a very interesting point, okay? The 3 kips per foot is something that we're going to need to deal with, and we're going to need to deal with it starting right here, but not after we rise up 80. Now, what he just said is we go down with a slope of 3 kips per foot. That's 100% correct, but let's game out what we're going to do here in a second. Okay, so this is point A, and this is point B. Somebody help me out. How much load is on the beam between point A and point B? How much is that? 120, right? This load right here, that is 120 kips because it's 3 kips per foot over a distance of 40 feet. Does everybody see that? So if I'm at 80 and I go down 120, where should I be? Negative 40. And how do I make that journey? I go like that, a straight line. Now, you had said 77, okay? Let me talk about that 77. I propose that the 77 is right here. How far away from this is the 77? 1 foot, exactly right. Because in 1 foot, I go down 3 kips.
Would that be, so you would find like the net if you had like a support and a point load at the same place, right?
Yes, I think we're on the same page. So let's see what happens. Let's continue this discussion. What happens at the 40, at the negative 40? Go down another 30. I drew my line there through that load, so that's probably a little difficult to see. My bad. So we go down another 30 to negative 70. And so now, what do I do from here to here? For how much? So 3 kips per foot for 20 feet is 60 kips. So if I'm at negative 60, or if I'm at negative 70, I go down another 60, what's that put me at? Let me just clarify that, because this is, hold on, I can do better than that. That is 60 kips. So if I'm at negative 70 and I go down 60, what's that put me at? And then at negative 130, I have a monstrous load upwards of 190 kips. That's a really big reaction. Negative 130 shooting up 190, what's that put me at? 60. And then now tell me what the shear diagram looks like from there to the end. What's it look like from C to D? Flat. Zero slope, because there's zero load. 0, and then the 60 brings me back home. Now, I'm going to stop for a sec because I want to see if this made sense. And if anybody has any questions about where these values are coming from. Now, when we construct the moment diagram, how do we do that? What do we need from this diagram in order to construct the moment diagram? Areas. Okay, let's start off with the really easy one. What's the area right here? That's 1,200, right? Okay. Now, let's ignore this right here. Let's ignore that for a little bit. Let's go to this. It's almost like that's a geometry problem that I just showed you. What is the slope of this line. And you don't need to do any math to figure out the slope of that line. It's, well, you're right, it's 3 over 1, but where's an easier place to find that? The load, exactly right. The slope of this line is the load, 3 kips per foot. Technically, that slope is negative because the line, I mean, that's a line with a negative slope. And why is the slope negative? Because the load is acting downwards, okay? So, help me out. How do we determine this distance right here again? How did we do that before? 80 over 3, right? Which was like 26.67. And this one, 40 over 3, 13.33 feet. So help me out. What is the area of that triangle, that first one? 1/2 base times height, right? 1/2 of 80 times 80 over 3. 1066.8, or if we're following our decimals, it'd be like 2/3, right? Is that fair? What about this triangle right here? What's the area of this? And it's negative, by the way. $266.67. Do I have a second on that? All right, so negative 266.67. Now, let's take this right here. Now, you could split this up and say that this is a rectangle and this is a triangle, or you could use the area of a trapezoid. The area of the trapezoid would be just average these two numbers and multiply by the width. It doesn't matter. We'll do the easy one. What's the area of the rectangle? Negative 140, or negative 1400. And this triangle, now the width is 20, what's the height? 60. So 60 times 20 over 2, what is that? So what do you get when you take that plus that plus that plus that plus that? 0. That's exactly right. Because the sum of moments is 0. What do we think? Does anybody have any questions so far? So the only thing left to do is to construct the moment diagram, and then we're done, which, so that we're crystal clear, because I know that this was a question, what is the absolute maximum shear on this? 130. Boom. The worst case, that's what I'm going to design the beam for, is that. That's the highest magnitude of shear that I see on the beam. Where'd my mouse go? There it goes. All right, so let's draw our moment diagram. Oh, I can do better than that. Okay, no, I can't. Okay, I'm not doing any better than that. That's what I'm doing. Okay, so before we start drawing stuff, let's see if we can figure out what our values should be or what they should look like. Now, I'm going to do something that's a little different that we had to do before. Notice how I've drawn my guidelines, like here, 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 and here. I'm going to draw another one. I'm going to draw another one from this. This one's new because this is where my shear diagram crossed the x-axis. Now, without drawing anything, we're not going to draw any curves or any lines or anything. Help me out, okay? I start at 0. What should my moment diagram be right here? Exactly. So I start at 0 and I go up 1066.67. Now I'm at 1066.67 and I drop what? And that puts me at what? There we go. So I'm at 800, and I'm at 800. Now, between here and here, what is the total amount that I drop? 2,000. So if I'm at 800 and I drop 12,000, drop 2,000, what's that put me at? Whoop. Negative 1,200. Does that make sense? And if I'm at negative 1,200 and I go up 1,200, that puts me back to 0. So before we draw anything, everybody okay with that? Okay. Now, let's start with the easy part. Let's start with this section over here. What should the moment diagram look like over here? A line, because that's a constant shear linear moment. And so we'll say linear. Ooh, we lost the calculator. Now, it's linear there. Where should it look everywhere else? Or how should it look everywhere else? Parabolic, right? These are lines. The integral of a line is a parabola. Now, this is where I want everybody to pay attention. This is kind of important. Watch this. Let's take this first region, okay? So let me put this over here. So this is 0. This is 1066.67. I propose that there's two options for this parabola. The parabola could either go like this, or it could go like this. How many vote for option 1? How many vote for option 2? Every one of you that voted for option 2? You're wrong. It's option 1. Let me explain why. Okay, the shear diagram is the slope of the moment diagram. What we've got here is, watch this, everybody pay attention. We have a shear diagram from here to here that goes from 80 to 0. Does everybody see that? So that means the slope has to go from 80 to 0. Do you see that? So this is a parabola that has positive slope that goes to 0. Does that make sense? Okay, if that makes sense, and I want one loud voice. This is 1066.67, 800, option 1, option 2. How many say option 1? How many say option 2? That's what's right. It's option 2. Because we're going, look right here. Now hold on, everybody watch. This is the shear diagram right here. Here, 0 slope. Here, negative 40 slope. So the line has to go from 0 slope all the way to negative 40 slope. It has to go like that. And here's the thing. This is all one continuous load. This is actually all one parabola. This is the relative maximum of that parabola. How do I know that that's where the relative maximum is? Because this is where the derivative is 0. The shear diagram is the derivative of the moment diagram. This is a relative maximum because the shear diagram equals 0 right there. Does that make sense? For the calculus fans in the room? Now, let's see, I'll use my same diagram over here. Now let's see if we're following along. So this final region, we go from 800 to negative 1200. Are we following option 1 or are we following option 2? How many say 1? How many say 2? How many are like, I want to get out of here? I'll just keep us in here for the next 20 minutes. Hold on. Seriously. Is option 1? Come on, everybody. Option 1, option 2. Okay, most people are saying option 2, and option 2 is correct. Because the slope, look what's happening. The slope is increasing in magnitude. If I were to go like this, then the slope would be decreasing in magnitude. I need a line that gets steeper and steeper and steeper as we go down, because the shear diagram gets bigger and bigger and bigger in magnitude. We go from 70 to 130. That, ladies and gentlemen, is your moment diagram. Now I want to stop for a sec because we got some split answers on some of this stuff. Please do not hesitate if this didn't make sense. And if it doesn't, let me know. I want to address it. I guarantee you, if you have a question about it, there's probably somebody else in here that does too. Yes, sir?
What would a case look like with the option 1?
The load could be going up. That's possible. That is one area where that's a possibility. That's the one that I could be thinking of right off the bat. There are other situations where that's possible, overhanging beams and whatnot. So, all right. Yes.
Can you just explain it again? Just why it goes this way?
Why it goes this way?
Yeah.
Okay. Everybody watch this. This is kind of important. It's not like this is going to show up on an exam or anything, you know. Oh, I got everybody's attention. So watch this. Yes, it will. Watch this. Okay, here's why it goes like this. Here's why it goes like this. What is the slope of the tangent line right there? I propose the slope is negative 70. And I'm getting that slope from right here. This is the slope of the tangent line right there. So over here, what is the slope of the tangent line right there? Negative 130. See, the reason it has to follow this pattern, is because this is the pattern where the slope follows this trend from negative 70 to negative 130. Does that make sense?
Yeah.
If it went the other way, the slope would be following the wrong way. The shear diagram would have to go up like that, and it's not doing that. This is a good stuff. I want to make sure that we're clear on this. Does that make sense?
Yeah.
Yes.
So if the slope went from the negative 130 to the 0, it would be that
Up like that. Yes. Does that make sense? If it doesn't, don't let me, like if the shear diagram went like from negative 130 to 70, then it would be flipped. Because again, keep in mind, all this is the derivative of that. So this is one of the reasons why the prereq for this class is calculus, not physics. So, what's that?
It's the second derivative of the top function there.
Well, yeah. Well, okay. So, this is the derivative of that, and this diagram here will tell you the concavity of the moment diagram. That's a true statement. You know, that's a 100% true statement. The load is negative because the load's going down, so the parabola opens downward. Both of the parabolas do. And what's the absolute maximum moment on this beam? 1200. That's what I would design the beam for, so that it doesn't fall down and kill somebody. And I wouldn't have known that if I hadn't plotted the shears and moments across the span. Does that make sense? Is everybody okay with that? Have fun with your homework. I will see you all on Friday.